Hello. In this video, I'm going to tell you about resonance forms. So resonance is a very important part of organic chemistry. I know I say that about a lot of things, but I do think that I say resonance in every other lecture that I give about organic chemistry all year long. Resonance forms tell us about reactivity of molecules in every kind of reaction, from acid-base reactions through electrophilic aromatic substitutions. The thing about resonance forms that a lot of students don't get is that it's a picture of a molecule. We live in a really complex world, and science is a complex thing, and a lot of the time we try to just forget that part, and we draw a molecule like this, butane. And when I draw this, I'm telling you there are two electrons. They're very well behaved, and they're living right between these two carbons. They are in line right here where I drew this bond. See? There they are. And for a lot of things in organic chemistry, it's okay to take that simplification to say, okay, there's two electrons, they live right there, they're holding those two carbons together. But a lot of the time, it's not safe to forget the complexity of the world. Okay, so if I change our example to make it butanoic acid, or sorry, this is just butanoate. Okay, I've taken off the proton. This is negatively charged. Again, we could look at this and say, okay, well, this oxygen is negatively charged, this oxygen is neutral, and everything else is neutral. But electrons aren't nicely behaved particles that live between two atoms. They're actually very small, massless wave things that sometimes act like particles and sometimes act like waves, and they may or may not be where I've drawn them. We can't actually know for sure, but we can use a theory that tells us where most of the electron density is at any given time. See, that's a way scarier way to think about a molecule, which is why most students don't do it. But it really is important, because just like the complex world around us, a lot of the time, a single drawing is not complicated enough or complex enough to encompass all of the reactivity of a molecule. So this molecule does not act as if only this oxygen was negatively charged and this oxygen was just sitting there. It really acts as if these electrons move up and these electrons move up. Okay, when we talk about resonance, we draw double-headed arrows to try to help remind us that these are resonance forms. And just like that, I've now made this oxygen negative and this one neutral. And so we also put brackets around resonance forms, because it's not the case that these electrons are actually moving. Okay, I have to draw them that way because that's our convention. I draw a double-headed arrow to show electron movement, and I'm explaining to you, okay, I'm showing you in our convention that these electrons are moving. In reality, this molecule exhibits complex behavior in which both of these things are true at the same time. What we really see reactivity-wise is both of the oxygens holding negative about 1/2 of the charge. Okay, but instead of drawing this, we draw this, and then we expect you to keep in your head that there's a resonance form, and it's going to react in the real world as if it looked something more like this. Okay? And so let's watch a short video about how these electrons move, okay, and what this resonance actually means, and we'll come back to some examples so I can show you how to think about this and in what cases it's going to be the most important for you. So this is a molecule that we're going to use to talk about resonance. And before we start the video, I just want to make sure that we're on the same page about what this molecule represents. So all the black balls are carbons. This carbon has a double bond to oxygen, then a single bond to this carbon. These carbons have a double bond, and then this carbon has a single bond to this carbon. Now this carbon looks red right now because it has 3 bonds and also a lone pair of electrons. So it is negatively charged. And if I was going to show you resonance with a curved arrow configuration, I would use a double-headed arrow to show these 2 electrons forming a new double bond between these 2 carbons. And then one of these pairs of electrons would go onto this carbon. Okay, and the animation is going to show mostly where the electrons are flowing. Okay, so where the negative charge is going. So we'll go ahead and start it. In the first step, the negative charge moves to that 3rd carbon, and a new double bond is formed. Okay? None of the hydrogens have moved. None of the atoms are allowed to move at all when you're doing resonance. Okay? Only electrons. And so we've moved that lone pair from this carbon, which I'm considering carbon number 4, okay? 1, 2, 3, 4. From carbon number 4 to carbon number 2. Now carbon number 2 has 3 bonds and a lone pair. It's formally negatively charged. But I have one more resonance form that I can go to. Those electrons can move also onto the oxygen. Okay, so if these electrons move to make a new double bond, the double bond that we had here moved onto the oxygen. So now the oxygen is formally negatively charged. It has 3 lone pairs now and a single bond. Okay, and so we can draw a valid resonance form where 3 different atoms are negatively charged. But really, what we have is a single molecule with a partial negative charge on all 3 of these atoms. Okay, all of these atoms are just holding part of the negative charge. None of them is actually holding all of the negative charge. And I also want to point out that these 2 carbons never had any negative charge on them. There's no valid resonance form that moves negative charge onto either of these 2 carbons. Okay, because of the flow of electrons, only these 3 atoms can hold the negative charge. So I'll let you watch that one more time without me really talking so you can see. Okay, so now the molecule has reset. All the negative charge is on this carbon. We can move it just by moving electrons to this carbon, and then we can move it again just by moving electrons onto this oxygen. So those are the 3 atoms that are holding the negative charge in the resonance form for this image. So resonance forms we can draw for almost any molecule, but it has the biggest impact if we have something that's charged. So let me draw us an example. So I've given us an example with a negative charge on a carbon atom. Now we know that carbon is not particularly electronegative, and so it does not particularly like to be negatively charged. And so if we can move that negative charge around, if we can draw a resonance form such that that negative charge is shared with other atoms, we can stabilize the entire molecule. And so what we're going to do, for something that's negatively charged, we're always going to draw 2 arrows at a time. Okay, we're going to move the negative charge, which is really a pair of electrons. And then we're going to have to move some other electrons so that we don't violate the octet rule. So let me just draw in some hydrogens real quick. Because first I want to point out that I cannot legally move these electron pairs in this direction. So legally move, let's talk about that for a second. There are a couple of rules. First, we need to remember that resonance forms all the resonance forms for a molecule are a complex of what that molecule actually looks like. So it's not that the molecule is going back and forth really quickly to different states. And it also means that we're not allowed to break any atoms off, okay? And so we're only showing the flow of electron density in a molecule. So if you find yourself starting to cut off an atom, you've done something wrong and you need to rethink. So in this case, if I tried to move my electron density in this direction, because I already have 8 electrons around this carbon, I would have to remove a hydrogen in order to not violate the octet rule. And so I can't do that, okay? That's against the rules of resonance. What I can do is move the electron pair in this direction. Now I can't stop here because I'm showing too many electrons around this carbon, but I can now move these electrons onto this carbon. And so now we need to draw the resonance form. We're always going to draw 2 arrows and then draw what we've made. Okay, another common mistake for students is that they try to do too much at once, and then they end up making mistakes. Okay, so go slowly. So what I have here now is a lone pair. I moved the 2 electrons that represent this double bond, and I put them right here. And that makes this carbon negatively charged. I have a single bond now between here and here, but I have a double bond between the next 2 carbons because I moved these electrons to make the double bond. And then I have a single bond out to that last carbon. And so this is the second resonance form. But I don't need to stop there. I can do another one. I can move these electrons to make a new double bond by moving 2 of these electrons onto the oxygen. If I draw that resonance form, it's going to look like this. This oxygen is now officially negatively charged. It had 2 lone pairs, and now by moving the electrons that used to be between this carbon and this oxygen onto the oxygen, it has 3 lone pairs, and that makes it negatively charged. I have a new double bond between that carbon and the carbon next to it, and then the rest is the same. Okay, so there's 3 main resonance forms for this molecule. We know then from looking at this that this negative charge can also be found on this carbon and on this oxygen. Okay, it's being spread out, it's being shared by all of those atoms. If we just looked at this, we wouldn't see that stabilization. Okay, the resonance forms show us how much more complex this molecule actually is. Okay, this is how it reacts in the real world. If we had started with a very similar molecule, but if we took out that inner double bond, okay, if we just started with this negative charge has no valid resonance forms. There's already 2 hydrogens here and 3 hydrogens here. And so I can't move these electrons without having to break a bond. I can't move them in this direction without having to break a bond. So this negative charge is much less stable than this negative charge because of resonance. So if we have a negatively charged molecule, we're going to draw 2 arrows and then redraw the structure. But resonance forms are also very important for positively charged structures, like this allylic cation. And I'm going to draw in my hydrogens for clarity. This carbon is positively charged because it has 2 hydrogens and 1 carbon, 3 bonds, 6 electrons, and a positive charge. Now we know that positive charges on primary carbons are very unstable, but this system has a resonance form. If we're starting with a positive charge, then we want to move electron density towards the positive charge. We're going to draw a single arrow and then stop and draw the structure. So So we'll draw a single arrow moving the 2 electrons in this double bond over. And that gives us a structure that looks like this. Now this carbon has an octet. It's no longer positively charged, but this carbon is positively charged. So that means, remember that resonance forms are different snapshots of the actual reactivity of a molecule. So this molecule reacts as if both carbons are always holding plus 1/2 of the charge. Okay. And something else that's really interesting that I'm not going to get into in this video, but resonance forms also show why when we have allylic cations, this carbon reacts like a cation and this carbon reacts like a cation, but the middle one never does. See, in both of our resonance forms, the middle carbon has an octet. It's never positively charged. And so even though this is kind of how it reacts, this middle carbon isn't positively charged. And so it doesn't react as if it has a positive charge on it. But that is a video for a different day. So resonance forms are challenging for students to look at in the beginning, but they're really, really important. Just try to keep them in mind as you do reactivity for the rest of organic chemistry, because resonance forms explain a lot of how we see small molecules react in the real world. Okay, so go ahead and practice these. Thanks for watching this video. I hope it helps.